Welcome to the 12th lecture on modern power electronics. For a while now, we have been discussing Module 2, which is based upon the design of various components of power electronic circuits, right from gate driver circuits to snubbers to heat sinks, and to the design of passives such as inductors, transformers, and capacitors. Today, hopefully, we will finish off with the design part of Module 2 by studying about the design of transformers and a brief discussion on the design of capacitors. Now, in the last couple of lectures, we have been discussing the design of inductors, which is closely related to the design of transformers. If we remind ourselves of inductor design, we know that it is based upon 4 constraints. The first constraint is the value of inductance that we require from the design, and it depends upon the number of turns and the effective reluctance of the flux path. By choosing an appropriate inductor core, we try to reduce this effective reluctance by means of a high permeability core and therefore increase the inductance within a small area. The second constraint is on the maximum allowable current that can flow through the inductor windings without causing the core to saturate. We know that it again depends upon the MMF equation and is closely related to the maximum flux field strength of the core as given in the data sheet. Of course, the area of cross section of the core and the effective reluctance. Very often we prevent the saturation of the core by slightly increasing the effective reluctance by incorporating a sufficient enough air gap within the length of the core. The third constraint on inductor design comes from which is a physical or a sizing constraint, where we ensure that if there are n number of turns and the wire cross section is AW, then it should be less than or equal to the total window area or the space within the core. Of course, the entire window area cannot be utilized, and there is some window fill factor as we have discussed below, so that also tends to reduce the effective area. And the total area occupied by the electrical conductor should be less than or equal to the effective window area. So this is a constraint on the sizing. And the fourth constraint of inductor design is based upon copper losses. And we know that while trying to minimize copper losses, we try to minimize the effective resistance of the inductor that we have wound. And we also know that the resistance depends upon the resistivity of the material or the conductor that has been used, the total length of the wire that has been wound upon the area of cross section of the wire. If you want to use a term that is more relevant to the geometry of the core, then we can use length per turn into the number of turns, because the length per turn will of course depend upon the width of the limb of the core. So once we had combined all these 4 constraints suitably, we came across an overall design equation, which was AC square, area of cross section of the core, into the window area, divided by length per turn. Again, this depends upon the the perimeter of the limb, and this should be greater than or equal to rho I max square upon B max square into the desired inductance value squared divided by R, and then you have the window fill factor or the utilization factor. So all these constraints, what inductance we want, what is the effective resistance of the copper loss that we can tolerate, what is the maximum current that should flow through the core without causing it to saturate beyond B max. All these are put within the same equation, and this constraint is eventually based on, this design equation is based on the sizing of the core. So we choose a size which fits in this equation, and matches all the four constraints. Now, the design of transformers is very closely related to all of these things. We are not really concerned about the inductance when we are designing a transformer, because there our goal is something else, which we will discuss later. But of course, we are concerned about the maximum allowable field strength in the core, beyond which the core will saturate. We are also we have a constraint on the sizing of the core by ensuring that the electrical conductor fits within the window area, and we are also concerned with the copper loss. So inductor design is closely related to transformer design is closely related to inductor design, because eventually we are doing with the same conductor material being wound around a magnetic core. Now, before we move on to transformer design, let's quickly discuss some basics of transformers. So we know basically a transformer can have a magnetic core, of course, with a closed path, such as a rectangular core or a toroidal core, or sometimes even an E-type core like this. Two E-type cores put against each other, and then instead of having one winding as in an inductor, we may have multiple windings, usually two or sometimes even more number of windings. So you may have a primary winding and a secondary winding, a primary and a secondary, and sometimes you may have a primary and then multiple secondaries wound over the other limbs. Sometimes the primary and the secondary may even be wound over the same limb as well. The only thing we are basically concerned with is that whenever I excite the primary with some electrical source and a current begins to flow, it establishes a flux in the core. The flux path should be such that it links the second winding as well. So that is our only constraint while designing transformer cores. Now, we know that when we are designing transformers, whether it is for the application in power electronics or from any other, for any other application, even for a line frequency 50 Hertz AC, the two main goals that we are concerned with while designing transformers is that we want electrical isolation. So the two circuits are electrically isolated. The primary and the secondary circuit are electrically isolated. However, they are magnetically coupled, or you can say that they deal with the same magnetic flux. And the second constraint, the second goal of designing transformers is to step up voltage or to step down voltage from the primary to the secondary. So whereas when we were discussing inductors, we saw that the primary job of the inductor was to we wanted to achieve some value of L that could store energy in the form of magnetic field. Here these two are our primary goals. Now let's consider an ideal transformer where we tend to neglect many things, such as copper losses and core losses in the transformer. They are completely neglected. We also assume that whatever flux is linked with the primary, it is equally linked with the secondary as well. So there is no leakage flux. There is no copper or core loss. There is no leakage flux. We also assume that the relative permeability of the core tends to infinity, or you can say that the effective reluctance of the core is 0. And basically we are just ignoring or neglecting any kind of magnetic or electrical losses when we are considering an ideal transformer. Now, if we go back to the fundamental equation governing a transformer, there is some analogous situation going on with inductors, capacitors and the like. For instance, I have a transformer with some primary winding wound on one limb and a secondary winding wound on the other, and a common flux is linking the two windings. Now, assuming that this is an ideal transformer, the same flux is linking with a primary as well as a secondary, and there is no leakage flux, then I know that if the voltage across the primary is V1 and that across the secondary is V2, then the basic equation governing an inductor is minus n d phi by dt. Or in other words, we can say that the winding associated with any flux establishes an EMF or voltage across it in such a way that it opposes any change in flux. Now let's see the analogous situation with inductors, which is simply V is equal to L di by dt. If I see an inductor, basically an inductor will always induce some voltage across it such that the voltage is induced in such a way that it opposes any change in current and tries to maintain a constant current through the inductor, right? Now, if you see it for capacitors, we know that I is equal to C dV by dt, which means that an inductor will draw into it, or it will, draw current in or out of it in such a way that the voltage across the or across the capacitor will remain constant. So a capacitor will draw in or draw some current in or out of it in such a way that the voltage across the capacitor remains constant, or dV by dt is minimum, right? Similarly, just the same analogous situation going on with transformers, that transformer windings, which are no longer dealing with just currents but with flux being associated with both windings, they induce EMFs. These windings, which are part of a transformer, they induce EMF across them in such a way that the flux across them remains constant. So d phi by dt is minimized. So your flux is constant. That is the operation of a transformer. Now, assuming that this particular transformer that we have drawn, it is an ideal transformer, then of course V1 will be equal to N1 d phi by dt, and just considering the magnitudes, and V2 will be equal to N2 d phi by dt. From this we know that since it's the same flux linked with both the windings, therefore V1 upon V2 is equal to N1 upon N2. So this gives us the second constraint of stepping up voltage or stepping down voltage by choosing the transformer turns ratio. So we generally tend to choose the turns ratio of these two windings on the basis of how much step up action or step down action we require. At the same time, we are assuming ideal transformer operation. So we also know that the input power is equal to the output power, or the power associated with the primary is equal to the power associated with the secondary. Therefore, I1 upon I2 is equal to V2 upon V1, which is simply equal to N2 upon N1. This also talks about the conservation of MMF. N1 into I1 is equal to N2 into I2. Now, having revised these basic concepts of transformers, I would also like to discuss with you transformers in power electronics applications. Now, mostly in power electronics, the voltages V1 that are, or V2 that are associated with the windings or the excitation voltages, they are high frequency PWM voltages. So it is very likely that the voltage across your primary or your secondary will be something like a PWM voltage, something like this, with a very high frequency. And when the voltage is positive, the flux will be increasing. So if I want to plot the flux, it will be increasing like this, and of course triangular in nature. And then the flux will be decreasing, increasing, decreasing, increasing, decreasing, increasing, decreasing, and so on. So when we're talking about power electronic transformers used in power electronic circuits, high frequency circuits, we are no longer dealing with low frequency sine waves, but very often we are dealing with very high frequency PWM signals, where the voltage signals are, some types of square waves, especially if you're talking about inverters or DC to DC converters, and the flux as a result of that is a triangular signal. And we know that V is equal to N d phi by dt, or you can simply say that phi is equal to integral of V by N into dt, right? Now if we try to solve for the voltage, let's say the primary voltage V1, it will be equal to N1, number of turns in the primary, into change in flux during a particular interval. So if the peak value of flux is, say, phi m, and the negative peak is minus phi m, so the change is minus phi m, so that is 2 times phi m in magnitude, and the time duration during which that change occurs is nothing but your total switching interval upon 2. So if this is Ts, if this entire interval is Ts, then this is, say, Ts by 2, if there is a 50% duty ratio assumed. So assuming a 50% duty ratio, we can say that the time interval during which the change in flux occurs is Ts by 2. This brings me to the equation of voltage across the primary being equal to 4 times N1. If Ts goes above, it becomes the switching frequency, into phi m, which is nothing but the maximum magnetic field strength, into the area of the core. You must have seen such an equation even while studying about transformers in AC circuits, just that instead of having the high switching frequency over here, you had the low frequency AC. It was that particular frequency was used over here. This equation also tells you that for a given operating voltage and a given number of turns, if you are increasing the frequency of flux variation or frequency of applied voltage, then naturally smaller sized cores can do your job, right? So you can use a smaller size of core because you're increasing the frequency for the same BM, for the same N1, for the same V1, of course, right? So this also tells us that when dealing with transformers in power electronic circuits, we tend to use very small ferrite core transformers which have tall and narrow BH curves, and we also look for cores which have very narrow hysteresis curves. So cores which have very narrow hysteresis curves, so that we are also minimizing hysteresis loss, because switching frequency is high, so you're going through or looping through that hysteresis curve again and again. So to minimize that loss, you use narrow hysteresis cores. That's why ferrite cores, small cores, because we need small cross section of the core, small ferrite cores with tall BH curves are used in transformers based on when you have to use them for power electronics applications. So this was about choosing the core and how the switching frequency is actually related to the area of the core. Another thing that you need to take care of while designing the transformers is the dot convention. So the dot convention basically tells you how you have wound the windings, right? So if you have, say, a rectangular core like this, and there is a primary winding that has been wound like this, so if you see from above, you have wound it in the counterclockwise direction like this, right? So the primary winding has been wound counterclockwise, and if I wind the same the secondary winding also counterclockwise, so it's like this. Something like this, right? So this is the secondary winding. Again, this has been wound counterclockwise. If you see from this direction, I'll be going counterclockwise, right? So both the windings have been wound counterclockwise. Now let's see, because every time I cannot draw the windings in such a way that even visually it is, understood whether it is clockwise, winding or a counterclockwise winding. Therefore, we use dot conventions to determine the direction or in which the primary and secondary have been wound. Now, assuming that I have excited the primary such that current is flowing in this direction, and since it has been wound like this, so the flux path is like this, right? Now let me just put a dot over here, so current is entering the dot. Now if I look on the secondary side, then my current has to flow. If of course a load is connected on the secondary, then some EMF will be induced in this winding in such a way that current will flow in such a way that it will oppose this flux, because basically from Lenz's law it will simply try to oppose whatever is the cause of change in flux. Now so if I look at how I have wound it from, this is my core, then I have wound it like this. So I want the current to flow like this so that it opposes the change in flux, right? Which means current is going from here and coming out of here, right? Or in other words, the EMF has been developed such that it pushes current from here, and this is the negative terminal. So if I had excited the primary winding by a voltage source that pushed current into here, then this terminal becomes positive and it pushes current out of here. So from dot conventions, if current is entering the dot on the primary, it will leave the dot on the secondary. Or in other words, both the dots will have the same polarity, right? Now what we know is that if both windings have been wound counterclockwise, then in that case, if the primary voltage is this, the secondary voltage will be phase shifted, or it will have a dot convention that shifts the phase voltage, like the secondary voltage V2 will be at 180-degree phase shift. So the dot conventions will be on the opposite ends. So current entering the dot on the primary means current leaving the dot on the secondary, or in terms of voltages, each dot has the same polarity of voltage, whether positive or negative. Now let's see the other dot convention. If we have wound the primary winding in counterclockwise direction, so the primary winding is, current is going into the primary like this. Like if this is the core, it is curling around like this. So flux is again in this direction. You have 1, 2, 3 like this, right? So again we have wound it counterclockwise. If this is the core, I'm going around the core like this. So if you see it from the top, you will see me going counterclockwise. So this is again counterclockwise, but this time we have wound the secondary in a clockwise direction. So in a clockwise direction means that I have wound it like this. So if you see me winding, I have wound it like this. Okay, so if you see from here, from the top, I see that my winding is going clockwise, right? And now let's see how the EMF will be induced. Now if some voltage source has been applied, and let's say this is my draw dot and the current is entering the dot, it will of course produce flux in this direction, right? And this particular the secondary winding will induce an EMF which will cause a current to flow that will oppose this flux. So in order to oppose, if the current flows like this, then the flux will be aided. So of course current has to flow like this, something like this, so that the flux is opposed. Now this also means that current entering the dot on the secondary side, this should reflect as current leaving the dot. So current is leaving the dot over here, or in other words, the dots have the same polarities of voltage. So of course the primary and secondary are in phase. There is no phase shift. Either by the windings you can cause 0-degree shift, or by changing the direction of the windings you can cause a 180-degree shift. So the voltages V1 and V2 are perfectly aligned. Of course their magnitudes will depend upon the transformer turns ratio N1 and N2. So this is another thing that you need to take care of while you are doing the transformer winding, that is the dot conventions. Now finally, let's talk about designing a transformer core. Now, when we are designing a transformer core, we have to take care of the turns ratio N1:N2, depending upon what is a step up or step down action that we require. We will also have to take care of the the dot conventions to make sure that the polarities are as per our requirements. Apart from that, there are two more constraints that we have to take care of. One is of course the constraint on the maximum current, depending upon the maximum field strength allowable in the core. Apart from that, also again we have two constraints. One is on the sizing of the physical constraint, or the sizing of the core, and trying to fit the electrical conductor within the core. So if this is my transformer core and this is my primary winding, if I cut through a cross section and I see that the primary winding is occupying some space with some number of turns, and I may have wound the secondary on the same limb itself, or I may have wound it on the other limb. In any case, the secondary conductors will also, they will also occupy some space. So with their own number of turns, right? So if this is the whole window area, this particular thing is your whole window area, you allocate some portion of this window area to the primary winding, and you allocate some portion of this window area to the secondary winding. It's not necessary that you give these allocations in equal ratio, 50%, 50%. We will see how we choose that allocation. Okay, so for now we know that we allocate, say, some portion alpha 1 of the total window area for winding 1, and the remaining, that is alpha 2, for winding 2. If you have a large number of windings, multiple windings, 3 or 4 windings, and of course you will have alpha 1, alpha 2, alpha 3, alpha 4, so on and so forth. But since we are considering only 2 windings, therefore alpha 1 plus alpha 2 will be equal to simply 1. So this could be like 70% of the area dedicated to winding 1, and obviously 30% remaining for winding 2, or 50% and 50%, so on and so forth. Now suppose this is the area of cross section of my winding 1, and it has n number of turns, n1 number of turns. Then total n1 number of turns into this area will be the electrical area occupied by the conductor. It should be less than or equal to the allocated area. So alpha 1 WA. But we have also talked previously about the window fill factor, which means that the complete window area cannot be utilized in winding the conductor, because some space will be occupied by the insulation, by the bobbin, by these empty spaces left between circles packed within a rectangular space. So all of these are going to eat up some space, therefore only some portion will be available for winding. Therefore another factor, that is a window fill factor or window utilization factor, comes into play. So this is for winding 1. And now if you have the other winding with N2 number of turns, which will have area of cross section of the wire, say AW2, if this is AW1, then it should be less than equal to the area that has been allocated for the second winding. Right? So this is our physical constraint. Earlier it was only on one winding, that was the inductor. Now there is a physical constraint on both the windings, the primary as well as the secondary winding, added to the fact that there are two windings which can completely occupy the window area. If you have more number of windings, of course these equations will, you'll go on adding another equation, and they will have alpha 3 and so on and so forth. So this is about a physical constraint on the sizing or fitting the electrical conductor within the magnetic core. Apart from that, we have another constraint, which is on the copper losses. And I have already discussed with you while doing inductor design that the copper losses will depend upon the resistance of the windings, right? So let me simply write the sizing equations on the right hand side, because I may need to use them again. N1AW1 should be less than equal to KW alpha 1 window area, and N2 AW2, this is the area of cross section of the wire or the winding or the electrical conductor, should be equal to KW alpha 2 into window area, and also alpha 1 plus alpha 2 should be equal to 1. So this is the sizing constraint. Now the resistance of the primary winding will be equal to the resistivity of the material that you're using, assuming the same material has been used, into the number of turns into the length per turn, so rho L, by area of cross section of the first winding. The second resistance will be equal to rho N2 LT upon AW2. If I look for the copper losses, the total copper losses, it will be the copper losses in the primary winding and the copper losses in the secondary winding. The copper losses in the primary winding will be equal to the primary winding current squared into the resistance of the primary winding, which is rho N1 LT upon AW1, and the copper losses in the secondary winding will be I2 squared into rho N2 LT upon AW2. So while taking care of the losses, the total copper losses of the windings, we have to take care of the cross section of electrical conductor in each winding, which we also know is related to the constraint on the sizing of the conductor. So we want to combine these two constraints together. So the total copper loss in the transformer winding will be equal to I1 square rho N1 length per turn. It will be same for both, the length per turn will be same for both the primary as well as secondary winding, because we are assuming that the limbs of the core have same perimeter everywhere. Okay, now the area of cross section of the winding, I can simply replace this equation over here. It becomes KW alpha 1 WA into N1 square. All right, and the second copper loss in the second winding will be I2 square into N2 square length per turn into window utilization factor into area allocated for the second winding. This gives us some thing to work upon. Now, the total copper loss will depend upon the number of turns, and there's a square over here, and the ratio of area allocation, and of course the currents flowing in the primary and the secondary. Also, we know that N1 I1 will be almost equal to N2 I2, so it is primarily which is alpha 1 and alpha 2 that is going to affect the copper losses. What I mean to say is that when you have a rectangular core and you have to allocate that this much area is for winding 1 and this much area is for winding 2, how do you distribute this area? You distribute it on the basis of the copper losses. So if I choose a very small alpha 1, then the copper loss will be very high in winding 1, and automatically this will become large, so the copper loss in the secondary winding will reduce. Now let's try to plot the copper losses. Say this is alpha 1 is equal to 0, or it could be maximum go up to 1, the entire window area being allocated for the primary winding. If alpha 1 is equal to 0, then the copper loss in the primary winding tends to infinity, and if it is 1, then it goes on, as you go on increasing, it goes on reducing and reaches a finite value at alpha 1 is equal to 1. So this is the copper loss of the primary winding. Quite naturally, if you see, as you are going to increase alpha 1 from 0 to 1, you are also decreasing alpha 2 from 1 to 0. So the green pen over here, it represents alpha 2. So this is alpha 2. Now when alpha 2 is equal to 1, that time the copper loss of the secondary winding is the minimum, and as you go on increasing it, when alpha 2 is equal to 1, when alpha 2 is equal to 1, it is minimum, and as you go on decreasing it towards 0, the loss increases. Finally at alpha 2 is equal to 0, this loss tends to infinity. So something like this. So the green one shows the loss of the secondary winding. The combined loss of the two, if you just add these up, will look something like this. And we try to find the alpha 1, or you can say the alpha 2 corresponding to this point. It's not necessarily 0.5. It's an optimization problem with a constraint. This is the objective function. You have to minimize it, and the constraint is alpha 1 plus alpha 2 is equal to 1. So this is, it's like an optimization problem that you have to solve and find the values of alpha 1 and alpha 2 in order to minimize your copper loss. So the area allocation कि आप एक कोर के अंदर जो स्पेस अवेलेबल होती है विंडो के अंदर, उसमें आप कितना एक वाइंडिंग को एरिया देते हो वाइंड होने के लिए, वो भी आपके कोर लॉसेस को डिटर्मिन करता है. सो ऑल ऑफ दीज थिंग्स आर you have to take into account, such as the core losses, how you allocate the areas. Also, while allocating the areas, you have to take care that the electrical conductor should fit within the window area, so you have to take care of the sizing. That is another equation. You have to also take care of the maximum flux density, just like inductors, and you also have to take care of the step up step down ratio, so n1 is to n2, and the dot convention as well, the selection of the core, choosing a small sized high flux density core such as a ferrite core. So all these things are very similar to inductor design, just that there is another set of winding and you have to accommodate it within the same core. So all these factors, you have to take care of these factors while designing your transformer Of course, and it's like an optimization problem. When you try to minimize your total copper losses, you find the optimum allocation of a window area corresponding to which your losses in the transformer core will be minimum. That's how you basically design high efficiency cores. When you say it's a high efficiency transformer, why do you say the copper losses are minimum? Because the areas that you have given to each winding, allocated to each winding, the cross section of the conductors that you have chosen, or the cross section of the core that you have chosen, you have made all these choices on the basis of various constraints like copper loss, and sizing and maximum flux density, etc. So that is a good design practice to design transformers, keeping all these constraints in mind. So this was about transformer design. I'll briefly go through capacitor design, because as you all know, the capacitors don't have to be really designed. You have to purchase them from the market. The only thing that you have to do while designing a capacitor is to choose the value of the capacitor and its voltage rating. So we have already discussed the design of capacitors in the last semester when we were doing applied power electronics for DC to DC converters. We have for almost every DC to DC converter we have designed capacitors on the basis of voltage ripple, right? So how much allowable voltage ripple, on the basis of that we decide the value of our capacitance, right? So C dV by dt is equal to I, and that's how you basically choose delta V, what is your maximum allowable ripple, and from that you select the value of your C. We have done these for DC to DC converters. Many times when you are designing capacitors for DC link, especially for DC link, where you have a three-phase AC supply, and then you may have a bridge rectifier or any front end converter that is converting this three-phase AC or single-phase AC into DC. Then you may have a DC link capacitor, and then you may have a DC to AC converter. I have discussed this previously also in our initial lectures. It's a very common topology, AC to DC and then DC to AC, where you will get control over voltage as well as control over frequency by means of this inverter that you are using, right? Many times in the DC link you use an electrolytic capacitor, whose size of course you determine on the basis of the ripple that you want in your DC link voltage. At the same time, sometimes there is another constraint that you take care of. Of course, the voltage rating of this will depend upon the maximum voltage that will be applied over here, which will in fact depend upon the peak line to line voltage and all those things. But sometimes the value of this capacitance is also designed for fault ride through. For instance, we know that the capacitor is an energy storage device, and we also know that the capacitor is maintaining its potential by means of this incoming AC source. Suppose somehow the grid gets disconnected, there is a power outage, and I want that my capacitor, it's an outage for a few cycles, an interruption for a few cycles, and I want that during this interval my induction machine or my drive or whatever load I am running on the three-phase side, it does not suffer, and the capacitor should be able to sustain it. Of course, the capacitor will be able to run my machine at the cost of its potential getting decreased, because now there is no incoming energy for the capacitor to maintain its potential. It's only losing its energy into the machine, and therefore its potential is falling. So for how long I want this capacitor to sustain this drive without causing the voltage to fall beyond some point, that is also sometimes used to design a capacitor. So the energy stored in a capacitor, we know that it is half of CV square, and nominally this voltage will have some value, V nominal, right? So nominally this is the amount of energy stored in this capacitor. If there is an outage, then the capacitor should supply power to the load, and in that process it will lose its energy and its voltage will fall. So it will lose some energy, and finally its energy will be CV, you can call it V allowable, which can be, let's say, 90% of V nominal or 80% of V nominal. I don't want it to go beyond that. So once it has lost its energy, an outage has occurred, it's feeding my load. Once it has lost its energy, its voltage has fallen to be allowable, and the total loss in energy is what has been supplied to this machine. So this is the loss energy before the outage, energy after the outage, half CV square minus half CV square. This is the energy that it has lost and supplied to the induction machine. So depending upon the the power rating of the induction machine, whatever was the power rating, and in this interval, what was the time interval for which I wanted to sustain the load even when there is an outage of the supply, that's how I choose the value of my capacitors. Sometimes they are also used for fault ride through like this. So if this is what is the nominal operating voltage, what is the voltage you can till which you can allow the capacitor voltage to fall, say 80% of the nominal or 90% of the nominal, and then for how long do you want to sustain, for 2 cycles, 3 cycles, 5 cycles of interruption you want to sustain your load and continue delivering rated power to the load. That's how you will find the value of C. So this is also about choosing the value of capacitors to supply the energy demand of the load for momentary interruptions, and of course voltage ratings depending upon in the circuits in which you have connected. Once you know the capacitance value and the voltage that it will be subjected to, you can simply purchase it from the market. There's nothing like design, as in like nothing that you have to do on your own, like in inductors where you have to wind, select cores, and wind optimally, allocate space and all of that. So that was about the design of capacitors, and with that we finish off design in power electronics. Now hopefully I suppose we should have a Google Meet session for now, where we can take up data sheets and explore various aspects of design, such as design of gate driver circuits. I'll share data sheets with you on each of those of gate drivers, and then design of snubbers, then design of heat sinks. We have discussed all of these, and in terms of passes we have designed inductors. Very similar to inductor design has been design of transformers, and lastly we have briefly discussed the design of capacitors, especially DC link capacitors, which are not only designed to minimize the DC link voltage ripple, but also to sustain or provide some fault ride through capability, sustain the load for a few cycles of interruption in the supply. So all of these we have discussed. Maybe we can have one online session where we can go through data sheets and try to see how much of devices, and try to see how much information by now we already know, and how much well acquainted we are with the design procedures. That's all for today. Take care, stay safe and healthy. All the very best. If you have any queries, please feel free to post in the WhatsApp group.